So today, what I'm going to do, since we're going to go over all the exam questions on Monday and Tuesday, what I'm going to do is to have a crash course in the topics uh, from right after the first exam, and just to remind you what they were about, so we can have a review of that of those topics, and so we will be prepared, or you will be prepared to answer questions uh, um, or answer questions from the old exams on Monday and Tuesday. So the beginning of so in actually so when uh, uh, first exam, or the material for the first exam stopped, we were still talking about the Hardy-Weinberg equilibrium. But instead of talking about Hardy-Weinberg equilibrium, the question at that point was deviation from equilibrium. And so everything we know about population genetics, or we have learned about population genetics thus far, is simply different ways by which a system would deviate from Hardy-Weinberg equilibrium. The first of which was so one, non-random mating. Okay, so in order to understand this, we just simply need to go back to our common system, common notation, having a two locus two allele system where you have A1, A2, A1, sorry, A1, 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 A2, and A2, A2, so it's one heterozygote, two homozygotes. And the idea being that how do the frequencies change over generations? So the first generation, if we have, so generation 1, you have p squared, 2pq, this should be squared, so let's fix this. P squared, 2pq, and q squared. The question is, how would non-random mating result in any deviation from the expectation? So the p squared, 2pq, and q squares, these are the deviations. And in the case of non-random mating, the simplest one would be to assume, so this is about non-random mating, so the simplest is to assume that it's about non-random mating between genotypes that are like each other. So similarity here is important. So the idea being that A1, A2 genotypes, they mate within themselves. It's selection for the same genotypes, and heterozygotes also, they mate amongst themselves. Now, what would be the effect of this method of reproduction, or this mating system? So let's. So the problem arises when you consider the fact that when A1, so A1, A2 tries to mate with another A1, A2, which is what should happen given the system we described. So the types of genotypes they produce, so this cross results in half of them being A1, A2, so half of the genotypes being A1, A2, 1/4 being A1, A1, and another 1/4 being A2, A2. So you can see why, because the gametes produced by A1, A2 genotype, they produce two types of gametes, A1 and A2, and they can create three different genotypes. They can, half of them would be heterozygotes, and the other half homozygotes. So the problem then is that at each generation you are going to have 1/4 going to p squared and 1/4 going to q squared. So the number of the frequency of heterozygous stages, the frequency reduces as this organism or the system evolves, since at every stage you're going to have pq divided by 2 moving to p squared and pq divided by 2 moving to q squared, thus making the frequency of heterozygotes in the next generation simply q and not 2pq, right? And if you keep doing that over generations, you're going to have a depletion of heterozygotes over and over again as you end up with more homozygotes. So that was the first example of the deviation from Hardy-Weinberg. So in this case, in a population with a mating system, you would have this reduction in number of heterozygotes as population evolves. The second one was the Volund effect. And the Volund effect simply, the idea was that sometimes, so you have subpopulations. I'm just going to assume that there are two subpopulations, subpopulation 1 and subpopulation 2, with their own allele frequencies P1 and P2. The problem or the phenomenon that is Volund effect is that at the population level, you simply have one frequency for P, right? So at the population level, we simply have this, right? But there are actually two subpopulations. The assumption being that you can't really see the subpopulations, so that they're cryptic in that they are not really easily identified. And the problem is, even if the subpopulations are at Hardy-Weinberg equilibrium, so they are in equilibrium, and so if you test the subpopulations, they show no deviation from Hardy-Weinberg equilibrium. But since at the population level you can't really see the subpopulations, if you use the p-value here, so this one, this simply would give you fewer heterozygotes than expected. So it would be fewer zygotes. So that would simply mean that you are going to have fewer of these, even though in reality you don't. You actually have no problem at all, because subpopulations are actually in equilibrium. So the Volund effect would result in a deviation because the population, even though it seems like a normal population, is actually subdivided into smaller populations, each of which in equilibrium, but when you look at the average allele frequency and you calculate the expectation, you observe that there are fewer heterozygotes than expected. So that was the second way that can happen. And by the way, as I go through it, whenever you have a question, just ask it. Don't wait until the very end. The third way, or the third method where you can see a deviation from Hardy-Weinberg is natural selection. Again, we can just go back to, natural selection. So we can go back to the original notation, which is the A1, A2, and A2, A2. And the allele frequencies are the p squared, q squared, etc. So, in the case of Hardy-Weinberg system, or actually, it's not a system insofar as it's just a model. Hardy-Weinberg model, there is no fitness, so everything has the same viability as every other thing. But in the case of selection, when you add selection, you have fitness values. And the idea is that for any and every genotype, so in this case, W11 is the fitness of the genotype, that is A1, A1, etc. And when you take into account the fitness, then the frequency in the next generation is going to be a function of the fitness. So it's going to be multiplied by the fitness. But fitness itself is not really informative, because the question is how much better or how much worse you are relative to the population. And in order for us to take that into account, we should consider the mean fitness, right? So in this case, or in every case, for that matter, what we do is we calculate the fitness, the mean fitness of a population, which is simply the fitness values for different genotypes multiplied by their frequencies, and divide the fitness of any genotype by that mean fitness and multiply it by the expected frequency. And we should get the expected frequency given selection. So that is simply how selection would work, because we introduce the element of fitness into the Hardy-Weinberg system. Now, one of the more important things is that the way fitness or the way selection works is by changing something or affecting something that we usually call delta P, right? Which is the mouse is a little bit funky. Okay, delta P. Delta P is simply the change in allele frequency. So in all these examples, we have two alleles, A1 and A2. P being the frequency of A1, 1 minus P would be the frequency of A2. Delta P is simply the change in frequency over time. And we can imagine simple scenarios where selection would change the allele frequency. For example, if we had a recessive allele that was beneficial, so it's delta P on y-axis, T on x-axis. It's going to be, it should be non-zero, but so recessive. Rare is going to eventually increase in frequency like that. If it is dominant, it's going to look like something like this. And if it is codominant, it's going to look like something like this. Okay, so the red one being recessive, the yellow one being dominant, and the gray one being codominant. And from this very simple plot, this time series, so time series meaning that it's a parameter, delta P, changing over time. So in the case of red one, actually interesting, because what it means is that if you have when you have a rare recessive allele that is beneficial, it is pretty slow at increasing in frequency. So selection has a hard time finding genotypes which carry that allele, but once present is pretty easy. to be selected for. So it slowly builds up, but then rapidly increases. In the case of dominant, as we can see, it's pretty fast. So all of them, so these three examples, so the recessive dominant, codominant, they all started from the same frequency, mind you. So in the case of dominant, as you can see, it starts pretty fast, but then it slows down. Simply because at some point for dominant alleles, the homozygotes carrying only the dominant alleles and heterozygotes carrying just one dominant allele, they both have the same fitness, so selection cannot distinguish between them. In the case of codominant, the fitness increases according to the number of beneficial alleles that you have. So homozygotes having 2 copies of the beneficial allele, they have the highest fitness. Heterozygotes, they have intermediate fitness, and homozygotes carrying the normal or neutral allele, they have the lowest fitness. So for selection, it's easy to select for the best genotype at any given point in time, and that's why it doesn't plateau or it doesn't slow down like the dominant case, but keeps going up until it just fixes. The other thing about selection, though, is that selection can result in some type of behavior. So we are still in part 3 selection. So selection can result in a behavior that is kind of weird, and that's equilibrium. So equilibrium, you can observe different types of equilibria under selection. So you can have stable, unstable, or neutral, or mixed, actually. Equilibrium. So what is that about? So we realized that if we look at some type of selection, so let's look at a case. So I'm just going to look at one case, that the other one would be easy to just be an extension of this. So we have 3 genotypes. Y-axis is just fitness, and a scenario in which the heterozygotes, they have the highest fitness, and then the 2 homozygotes, they have relatively lower fitness values, right? So it's a bar graph where the highest fitness is right here in the heterozygotes, and the 2 other homozygotes, they have lower fitness. The question is, if you have a system like this where the fitness values are such that heterozygotes are better than the homozygotes, how would the frequency of the allele A1, which would be P, would change over time? And it turns out that if you start evolving from low frequencies, you're going to reach to some value and stay there. And if you start from high frequencies, I mean, not 1, but below 1, but pretty high, you're going to converge to some other value. And this point determines the equilibrium of the system. So the gray line is the equilibrium. So the idea being that since the heterozygotes are the best ones, if you have, you need to have the both types of alleles to maximize the number of heterozygotes in the population. And for that to happen, a selection is if one allele is pretty low in frequency, like this one, selection is going to select for it to increase in frequency. If the other allele is pretty high in frequency, selection is going to select against it. So its frequency decreases. In either case, the idea is that you have frequency. You have to maximize the frequency, I mean, relative to the fitness benefit of the heterozygote. So this should be maximized. Again, depending on how much difference is between the fitness values, the equilibrium is going to move up or down on the y-axis. But the idea is that you need to have more of the heterozygotes that are pretty good. So selection is going to select for this. Okay, selection. This. It's actually kind of interesting to look at the way this plot, so the time series, can be converted into a delta p versus p delta p. This mouse is pretty weird. What is this? Okay, delta p versus p. Let's say. Okay, let's say here is 0. So below this line, everything is negative. Above it is positive, and our equilibrium is here. So this one is P hat. So as you know, as you put the square line on top of P, it becomes the equilibrium values. Now, so how does P changes when P is low? So as you can see from the time series, so because selection is selecting for heterozygotes, since they are the better ones, if you have low frequencies of P, it should increase. So it's going to be a parabola like this, showing positive. And when you're higher than equilibrium, selection is going to select against you, so you're going to have a negative delta P. So it's a parabola below this 0 line, so it's a negative. So at below equilibrium, you have positive delta P, and above equilibrium, you have negative, which makes sense because the time series also tells us that when you are below, you're going to decrease. When you're above, you're going to increase. Now, aside from so this is equilibrium, but selection also, and this equilibrium is due to simply selection. So there's a selection for a genotype, and that selection is going to determine how the system behaves. But you can have slightly more complicated modes of selection as well. Although I shouldn't say it's not complicated, like it's also the same, very similar ones. The similar ones are where the fitness values are actually not fixed. So here we're looking at the fitness, and then on the y-axis it's fitness, on the x-axis the frequency. Let's say the frequency is the frequency of A1 allele. So thus far, whenever we have been referring to the frequency and the fitness, there was no relationship really. So A1, if A1 is beneficial, is going to be beneficial by the same amount, regardless of how prevalent it is in the population. So the fitness is a straight line. I mean, it's sort of a straight line over the range of frequency available. So from 0 to 1, which is the logical range of frequency, the fitness value is a fixed number. But it can be positively correlated, meaning that when you have few copies of A1, the fitness is low. When you have more of them, the fitness is high, or the other way around, which is the frequencies. The fitness is high when it's rare, when it becomes dominant in the population. It's not as good like the mimicry case, which we have talked about so many times. So that is another way by which selection is changing the way we think about it. So not only, unlike Hardy-Weinberg equilibrium, Hardy-Weinberg system, we have fitness, but the fitness is also changing over time, although in a way that is very systematic. It's just not a chaotic change in fitness values, but a response or fitness being a function of frequency. In addition, we have mutations, which we didn't have in Hardy-Weinberg equilibrium. There were no mutations there. And what is the deal with these mutations? Now, mutation is interesting insofar as it relates to different evolutionary forces that work, and selection is one of them. So let's assume one case where you have with a probability u A1 becomes A2. Right, so that's how mutation works, right? So there's one allele mutates into another one. And what if the allele A2 is a deleterious allele, right? So A2 is a bad allele. So you would expect selection to select against it, right? So you have selection here acting negatively. So let's add a actually just write selection against that. Right. So you have selection against A2 if A2 is deleterious, which in this case it is, but you have a constant flow of A2 into the population fueled by mutation rate. The mutation rate being U, so it's a one-directional mutation, so you don't have the reverse process for the sake of simplicity. So what we end up having is change in the frequency of A2, which we usually use Q, is actually two things. It's the change in frequency of Q through mutation, so it's delta M Q, and you have another one which is the change in frequency of Q due to selection. So S Q. And as you can see, one is trying to get the frequency down. So the delta SQ, because selection is against the allele, is going to decrease the frequency of A2, while delta MQ is going to be a positive number trying to increase the Q, right? And these two values, so delta MQ and delta SQ, at equilibrium, they should be 0, right? So at equilibrium, you should have the an equal change in Q fueled by mutations and a similar a reduction in Q fueled by selection. And if you do a little bit of math, which you're not going to do here, you realize that at equilibrium, the frequency of Q is roughly something. So that something is mutation rate, the square root of mutation rate, minus the fitness of the homozygotes, carrying only Q, which is A2, right? So is 1 minus W2 2. This equation is actually so. This is applicable when W22 is not 0. So if W22 is 0, you're going to just reduce that. So exclude W22. It would be U divided by 1, which is U. So it would be a square root of U. And this one applies to the recessive ones. So whenever you're dealing with dominant deleterious or dominant lethal alleles, you just get rid of the square root. So it becomes mu divided by 1 minus W22. Or in the case of dominant lethal, it's simply mutation rate. It's U. And in this case also, mutation rate is changing the allele frequency, but selection is acting against it. So what other major force or mechanism is there for us to consider in relation to a real population genetic model that is not Hardy-Weinberg equilibrium? And that forces drift. So you have mutation, selection, and drift. And selection and drift are actually very important because they usually act against each other. One property of the drift, and so in the Hardy-Weinberg equilibrium, we knew that the population was considered to be an infinite population. But drift, the whole point is that it's a finite population. So in any real system, you would have to deal with drift because except for the mathematical, theoretical populations, real populations are composed of individuals, and individuals are finite entities, and you can have a finite number of them in a population. And one of the first revelations from this topic is that if you were to look at the heterozygotes, so again, our usual notation is FA2, which we also refer to as H, which means heterozygosity. If you look at the process, if you look at the number of heterozygotes over time in a finite population, so this y-axis is H, x-axis is T, meaning time, the number declines, or the proportion declines, and the decline is relative to the population size. So as population size increases, the decline becomes less pronounced. Okay, so let's so as population size increases, the line becomes more horizontal. But this is not is no mere population size. It's actually what they refer to as the effective population size. As effective, it's like a kind of a tautology in relation to heterozygosity, because the effective population size in its formal definition is defined as a population that shows a decline in heterozygosity that corresponds to our expectation. And real populations are not like that. So real populations, so in a effective population size, the idea being that everyone mates with everyone else, and there is no discrimination during mating. So everyone can potentially mate with everyone else. There's no preference really. But in a population that is a finite population, we expect the heterozygosity to change like this. So H prime is the heterozygosity in the next generation, H being heterozygosity in the current generation. That would be multiplied by 1 minus 1 over 2n. 1. Writing with this mouse is pretty rough. N. I'm sorry for this weird N. This is some sort of a expressionist painting at this point. But you see the idea. So the idea is that the loss in heterozygosity is going to be proportional to the inverse of population size. So as population size becomes bigger, the change in heterozygosity is going to be more minute, and as population size decreases, the change is going to be much more pronounced. Now, there's a good reason for us to consider this, because it turns out that if you had a neutral allele in a finite, it had any allele actually. So we're just going to talk about the beneficial and neutral alleles. So in a population of 2n individuals, these are diploids. That's why usually it's 2n, because each individual has 2 sets of chromosomes. So if you have a single copy of an allele, so a single mutation, the probability of you going to fixation, so it's the probability of you spreading to every individual in the population, is 1 over 2n, which makes sense because there's 1 in a sea of 2n individuals, or as 2n copies. So the probability of you being picked is simply that frequency. For beneficial alleles, though, it can be reduced to just S, so the selection coefficient. So how much beneficial is the allele is going to determine how likely it is for that allele to go to fixation. Now, it turns out that if the population size, so that way the population size multiplied by 2, again, this is the effective population size, multiplied by S, which is the selection coefficient of the allele, is much smaller than 1, that allele is going to be effectively neutral. So if this is the case, then the probability of that allele going to fixation is 1 over 2n, and not selection coefficient. So this is not going to be not this one. So I'm going to cross that, but the other one, right? So you see what happened, right? So it's either population size that is a moderate population size, but the effect of the mutation is pretty tiny. So it's a slightly beneficial mutation in a moderately sized population. It's likely for that allele to be effectively neutral, but for an extremely, I mean not extremely, but moderately beneficial allele, if you put that allele that would normally go to fixation in a normal sized population, if you put that allele into a smaller population, or a small enough population, that allele would be effectively neutral. And that's the whole point of how selection and drift interact with each other. This equation simply tells you how they would interact. accordingly, right? So you can effectively turn a beneficial allele into a neutral one by pure drift, which is another word for population size. Which brings us to one thing I forgot. There's also the idea of the how long does it take for alleles to go to fixation. Again, the derivations are not important, but for a neutral allele is 4 multiplied by n, and for beneficial allele is more complicated. It's a 4 natural logarithm of 2n divided by selection coefficient. So again, these are the average time it takes for neutral, which is 4n. Again, this is the average time, so it can take shorter or longer, but on average, it should take that much time for a neutral allele versus a beneficial. So beneficial one in a moderately sized population should go to fixation much much more quickly compared to a neutral one, which again stands to reason. Now, we talk about drift and selection, and that inevitably brings us to the idea that there are two schools of thought in evolution. There is selectionism, proudly represented by. Actually, I wouldn't consider myself selectionist. I'm probably neutralist then. Neutralism. Actually, these days they're not really that. It used to be pretty brutal in the 70s, 80s, but nowadays we know that everything is like it's partly selectionist, partly neutralist. They're not really contradictory at all. So the idea was, so for the selectionist, what was the question? The question was, why do we see heterozygosity, right? So both of them try to explain why there is heterozygosity in populations, right? So H was the common, the common issue that they were trying to address. And in case of selectionist, you can easily as Jennifer said, T. No, so T, the average time of fixation for n is for a neutral allele. So in selectionist, the idea was that, well, how do you explain heterozygosity? The standing heterozygosity, the heterozygosity that you see in populations. And it's actually pretty easy, even you can explain it, because when there is heterozygote advantage, selection keeps heterozygotes in the population because there's selection pressure for them to exist. In the case of neutralists, though, that's less clear because, as we know from the loss of heterozygosity in a finite population, if it's purely neutral, heterozygosity should go to 0 eventually. So what they proposed was that we are just looking at the transient change in heterozygosity. Like eventually they're going to go to 0, but we are just looking at systems while they're evolving. Now, the ramification of these two theories that, so if we define the rate of evolution as two, again, these are diploid populations, that's why there's always two. So K being the rate of evolution, if it's 2n multiplied by mu, which is the mutation rate, multiplied by I have no pi, which is sort of this probability of fixation. So if we define the rate of evolution as such for a neutral one, so K n, it should be, so we know that for, so it's 2n multiplied by mutation rate. So the probability of a neutral allele going to fixation is 1 over 2n, right? So if you use this, you realize that the rate of evolution is going to be, so this one cancels with that one. So you simply have mutation rates as the rate of evolution. So the rate of evolution in the neutral case is going to be constant, a constant process, which is specified by the mutation rate. In the case of a non-neutral evolution, it's going to actually have to calculate the probability. And this, so what does it mean? It means that at least where we know that there is no selection, so there is actual neutral evolution, the rate at which those regions of the genome change is a constant change. So it's like a clock ticking over millions of years. You get mutations in those regions at a constant rate, and that allows you actually to do something rather magical, which is to compare. So we're going to use the notation in your book, which is the DAN and DAS. So DAN, DS, and that's kind of confusing because so DAS is S standing for synonymous substitutions. So it's the rate at which synonymous substitutions happen. And as you know, by definition, synonymous substitutions are going to be neutral, right? So DAS is neutral evolution. Which should, in principle, be a constant process. DAN, on the other hand, is non-synonymous, so those are alleles or mutations that would have a fitness benefit or fitness cost. So that would be a selection or an index of selection. So DAN is going to show selection for you or represent selection as it relates to different regions of the genome, and DAS is going to represent neutral evolution. As we just proved from this rate of evolution K, when you try to calculate the rate of evolution for neutral alleles, it's going to be a simply mutation rate. So the neutral evolution becomes a reference point. So if DAN is the same as DAS, so the rate at which non-synonymous substitutions happen is the same as synonymous one, or have been, then it means that practically there was no selection. It was just purely neutral change, so no selection at all. If it's positive, it means that there was more change in non-synonymous versus synonymous, so it's positive selection. So selection was trying to find something. It was positive because more substitutions that were non-synonymous became fixed in the population. And if it's negative, it means that there have been fewer non-synonymous substitutions relative to synonymous ones, meaning that selection selected against a lot of these non-synonymous substitutions, implying that there was negative selection against something, probably some evolutionary constraint or what have you. So thus far we covered everything. Right before the evolution had multiple on multiple loci, the evolution on multiple loci, I actually discussed it last week. So I'm not sure. We don't need to go over this because the haplotypes. So what we are going to do on Monday will be to go over the exams and finish the job and answer all the questions left on those 4 exams relevant to our discussions. And by that time, I think you will be ready to just crush it. I mean, by it, I mean the exam. So any question, any comments? Again, this recording will be available